Now that we know how to find eigenvalues and eigenvectors, I want to show you how to use that to diagonalize bigger matrices. In the previous section, we talked about how to diagonalize a small upper triangular 2 by 2 matrix, but anyway, so this video is going to be dedicated to just diagonalizing a 3 by 3 matrix, essentially, along with a theorem and corollary. So here's a theorem. Let lambda 1 through lambda n be distinct eigenvalues for a matrix or a linear map, and let b1 through bn be the associated eigenvectors. The theorem says that, given this, the set b1 through bn is a linearly independent set. Sorry about that. So the key point is that lambda 1 through lambda n are distinct eigenvectors. So sometimes you might have that the characteristic polynomial factors as x minus 1 times x minus 2 squared. This theorem does not apply in that case. So because the eigenvalues are excuse me. So the theorem could apply there, but you would only get lambda 1 is 1 and lambda 2 is 2, and so you'd only get like two linearly independent eigenvectors there. Even if lambda 2 has eigenspace having dimension 2. So anyway, more importantly, the following corollary gives us one way to automatically say that a matrix is diagonalizable. So if you have an n by n matrix with n distinct eigenvalues, then that matrix is automatically diagonalizable. So let me remind you of a lemma from the previous section. The lemma says that a linear map f from V to itself is diagonalizable if and only if there's a basis B consisting of vectors b1 through bn and scalars lambda 1 through lambda n, such that f of bi is equal to lambda I bi for all I. I could rephrase this lemma to say that a map or a matrix that is diagonalizable if and only if there's a basis B for V or Rn or whatever consisting of eigenvectors corresponding to some eigenvalues. So in particular, this set has to be linearly independent and span the entire space. So being linearly independent is basically, for this corollary, covered by this theorem. So the corollary says that all right, well, assume that you have n distinct eigenvalues. Then by the theorem, you would get n eigenvectors associated with it, and that set of eigenvectors would be linearly independent. And then for an n by n matrix, that represents a map from an n-dimensional vector space to itself. So you have a linearly independent set consisting of n vectors for an n-dimensional vector space. Therefore, that has to be a basis. So you have a basis of eigenvectors. And the lemma says if you have a basis of eigenvectors, then you're diagonalizable. And so the corollary just falls right out from there. So anyway, the rest of this video is just going to be the following example. Diagonalize this matrix. So if I were you, I would stop the video and I would just try to diagonalize this matrix on your own, given the tools that you already have been given. So nothing that I'm going to do in this example is going to be something that we haven't talked about already, except for maybe a factoring thing here or there. But anyway, try and find the eigenvalues and eigenvectors for this matrix, and then see if you could diagonalize it from that. Okay, so I'm going to assume that you've paused, and I'm just going to proceed. So, all right, if I want to look for eigenvalues. That's what I want to do first. I want to first find the determinant of A minus lambda times the identity matrix. Okay, this looks good. I'm going to expand along the first column because I have a 0 there. So I'm going to get 2 minus lambda times 1 minus lambda times 3 minus lambda minus 8. And then minus 0, and then plus negative 4 times negative 2 times 1 minus 2 times 1 minus lambda. I don't know if I'm doing this too fast or not, but this right here is just the determinant of this 2 by 2 matrix right here, and this right here is the determinant of this 2 by 2 matrix right here. Okay, what is this? This is 2 minus lambda times 3 minus 4 lambda plus lambda squared minus 8. I'm going to distribute this negative 4 plus 8 times 1 minus lambda. This is negative lambda cubed. I don't want to jump ahead too fast. Yeah, I do. Let's do it. Wait, this is minus 8. So minus 8 plus 3 is minus 5. So let's do that. Okay, so now distribute the negative lambda to this. So I get negative lambda cubed plus 4 lambda squared plus 5 lambda. Distribute the 2 and I get plus 2 lambda squared minus 8 lambda minus 10. And then plus 16 minus 8 lambda. Okay, let's combine like terms. I'm seeing 6 lambda squared minus 3 lambda. Oh wait, minus another 8 lambda. So this would be minus 11 lambda. Right, so I have 5 minus 8 minus 8. So that's equal to negative 11 lambda. And then what about my constant terms? I have negative 10 plus 6, or plus 16. So that's plus 6. Okay, how do I factor a degree 3 polynomial? So there's no good answer to this, but one way that you could factor a degree 3 polynomial is to first look for roots. So let's look for roots to this thing just by plugging in small numbers and seeing if it spits out a 1. So if I were to like plug in negative 1 into this, plus 6 times negative 1 squared plus negative 11, negative 1 plus 6. I want to know like whether or not this is equal to 0. So in this case, I would get like negative 1 plus 6 plus 11 plus 6. So this is not 0, so negative 1 is not going to be a root. So let's actually just completely get rid of that. The idea is that if you can find a root, then that tells you one of the factors of your thing. So let's plug in positive 1 and see if that works instead. So I get negative 1 cubed plus 6 times 1 squared minus 11 times 1 plus 6. And this is 12 minus 12. So this is equal to 0. So positive 1 is a root. Which actually tells us that lambda minus 1 is a factor of negative lambda cubed plus 6 lambda squared minus 11 lambda plus 6. And so I can just do long division of polynomials and just figure out how this actually would factor. So let's do that. Maybe you're not familiar, or maybe you haven't done this in a while since like your algebra class, how to do long division of polynomials. But so this will maybe be a refresher, or maybe you're learning it for the first time. Hopefully not. Okay, so what do we do? So you work from highest degree down. So I have a negative lambda cubed right here, and I look at the highest degree term of the thing I'm dividing this whole thing by, which is lambda. So how many times does lambda go into negative lambda cubed? Well, lambda times negative lambda squared is equal to negative lambda cubed. So the answer to that question would be negative lambda squared. So now I just multiply, I multiply this times lambda minus 1, and then I subtract that from this whole polynomial up here. What do I get? I get negative lambda cubed plus lambda squared. And now I want to subtract this whole thing. So what do I get? Okay, so this will be a 0 right here. And then here I'm getting, so plus minus 6 lambda squared minus lambda squared, that'll be 5 lambda squared. And I just bring down everything else. Okay, now how many times does lambda go into 5 lambda squared? Well, it goes in 5 lambda times. So 5 lambda times lambda is 5 lambda squared. And then 5 lambda times negative 1 is negative 5 lambda. And I subtract all that. And what do I get? I get negative 6 lambda plus 6. And then how many times does lambda go into negative 6 lambda? Negative 6. So I get negative 6 lambda. Negative 6 times negative 1 is positive 6. And I subtract all that, and I'm left with 0. So my remainder is 0, so this is definitely going to be, this is actually going to factor as this. So this whole polynomial right here, which is in double red now, it factors as lambda minus 1 times negative lambda squared plus 5 lambda times, or minus 6. Okay. So our characteristic polynomial is now equal to lambda minus 1 times negative lambda squared plus 5 lambda minus 6. We can factor out a negative 1. Lambda squared minus 5 lambda plus 6. And then this factors as lambda minus 2, lambda minus 3. Great, so now we have our eigenvalues are 1, 2, and 3. Eigenvalues. Okay, let's find our eigenvectors associated to it. One nice thing about diagonalizing is that we only have to find one eigenvalue associated to our eigenvector. We don't have to find the entire eigenspace. We could just find one solution to ax equals lambda x. Okay, so let's do it for lambda equals 1 first. I don't remember what a is. Let's just copy and paste that. Here's our a. A minus lambda I is equal to, so lambda is equal to 1. This is equal to 1, 0, negative 4, 8, 0, negative 2, 2, 1, 2, 1, 0. Okay, cool. Let's do 4 row 1, add it to row 3. get 0, also 0, and then 8 plus 2 is 10, and then -2 row 2, add it to row 1, and -10 row 2, add it to row 3, okay. So here I get x minus 2y is equal to 0, and z is equal to 0. So x is equal to 2 times y, and z is equal to 0. So we only need to pick one eigenvector for this eigenvalue. So let's just pick y is equal to 1. That would make x is equal to 2 times y, which is equal to 2, and then z is, of course, equal to 0. So then x, y, z, so this is going to be our b1. It's equal to x, y, z is equal to x is 2, y is 1, z is 0. All right, so that's our first eigenvector. This is for lambda equals 1. And if I wanted to go, so, all right, 2, 1, 0. If I wanted to multiply a times 2, 1, 0, hopefully I get lambda times 2, 1, 0. So, all right, 4 minus 2 plus 0, so that's 2. 0 plus 1 plus 0. -8 plus 8 plus 0, that's 3. So I get 2, 1, 0, which is equal to 1 times 2, 1, 0. So this works. So that is an eigenvector for our eigenvalue 1. Okay. Here's our A again. Now we're doing it for lambda equals 2. So A minus 2i would be 0, -1, 1 along the diagonal. Okay. Let's do 2, row 2, add it to row 1. Well, -2, actually. And then that'll be a row of zeros now. Perfect. And then let's do 8, row 2, add it to row 3. So this would be a 9. Okay, and that's good enough for me. I'm just going to say that this tells us -y plus z is equal to 0, and -4x plus 9z is equal to 0. So I have y equals z, and then 4x equals 9z. Okay, so I just need to pick one thing. So if I pick x is equal to 9 and z is equal to 4, then this equation right here would be satisfied, because I would have 4 times 9 is equal to 9 times 4. So that would work. And then y is equal to z. Z is 4. So that'll be 9, 4, 4. So B2 is going to be equal to 9, 4, 4. So that's our second eigenvector, B2. This is also for lambda equals 2. Usually I label the b's by just like first b, second b, third b. I'm not doing it like according to like lambda equals 1, lambda equals 2. I don't know if that's like unclear or not. Just to clear that up. Doesn't really matter. Okay. If I do a times 9, 4, 4, do I get the right thing? 18 minus 8 plus 8, so I get 18. 0 plus 4 is 8. -36 plus 32 plus 12. So this is 18 8, and 44 minus 36 is 8. This is equal to 2 times our vector b2. So that's perfect. Works. Okay, copy our a down again. Let's do lambda equals 3. A minus 3i is equal to the following: -1, -2, 0 along the diagonal. Let's do -4 times row 1, add it to row 3. So I get 0, 16, and -8. Okay, that's useful because now I could just do 8 times row 2 to clear out all of row 3. So -1, -2. Actually, I can just go ahead and clear out some stuff above row 2 as well. So this will be -16 plus 16, and then -8, or 8 plus -8. Okay, and I'm also going to do negative row 2, add that to row 1, and then that'll be 0, and that'll be a 1. So I get -x plus z is equal to 0, and -2y is equal, plus z is equal to 0. So x equals z, and then 2y is equal to z. And then z is free. So let's pick y is equal to 1. Then z would be equal to 2 times y, which is 2. And then x would be equal to z, which is also 2. Okay, so I get b3 is xyz, which is 2, 1, 2. And to double check that we're right, let's just go up to a, multiply by 2, 1, 2. So I should get 6, 3, 6, because it's equal to, I want it to be equal to 3 times our vector. 2 times 2, so I get 4 minus 2 plus 4. 4 minus 2 is 2, plus 4 is 6. Good start. 0 plus 1 plus 2 is 3. -8 plus 8, that's 0, plus 6. What happened here? That's the 3. Okay, cool. So that works. So that's equal to 3 times 2, 1, 2. So I am confident in our answers. So this is for lambda equals 3. Okay. And now we are pretty much done. So this tells us that rep b to b of, do I have a function f? So let's say that like f of vector is equal to a times vector. So f is the function such that a is equal to the representation of f with respect to the standard bases. Then rep b to b of f is equal to, well, where b is equal to b1, b2, b3. And then this is the diagonal matrix with our eigenvalues along the diagonal. And then, so A and this matrix, which I will now call, let's call it D for diagonal. These differ by a change of basis matrix. And what is that change of basis matrix? So let's look at the diagram so that we can, so oftentimes when you're told to diagonalize a matrix, you're really being asked to write, find an invertible matrix P such that PA, P inverse, is equal to a diagonal matrix D. That's often what you're really being asked to do when you're being asked to diagonalize something. So let's do that. And let's use the diagram to do this too. So we're in R3. So with respect to the standard bases, R3, E3, A. So the reason I put like the standard bases here is because I have A is just like our standard matrix. So A represents matrix multiplication, as I said before. So this is like the map F right here. So yeah, A represents that map F that I just described with respect to the standard bases. And then I do R3 with respect to B, R3 with respect to B. This is my diagonal matrix D. And let's say, so if I want, let's say that A is, so the D is equal to matrix times A times matrix inverse. So this will be, all right, so let's make this one our P, and this one will be our P inverse. I want this one to be our P because the standard basis, why is that? That should be a 3. Okay. This will be a P because this thing is easier to find, and then the P inverse would just be the inverse of that matrix. So P is equal to the representation of B and E3 of the identity. It's the change of basis matrix from B to E3. This consists of our eigenvectors B1, B2, and B3. And so let's go find what those were. So B1 had 210, 944. And then what was our last one? 212. So this is our matrix P right here. So according to this diagram right here, D is equal to, so I first multiply by P on the left, then on the left by A, and then by P inverse on the left. So we read from right to left because you're multiplying on the left. P, A, P inverse. Right, first by P, then by A, then by P. Yep, okay, this looks good. Okay, so then I get that 1, 2, 3 along the diagonal is equal to this matrix P times A times P inverse. I'm not going to go through the process of finding the inverse of this matrix. The inverse exists because B1, B2, B3 forms a basis. That's fine. Not going to go through it, but just know that you can diagonalize A just by multiplying PA, P inverse. And if you do this whole matrix multiplication out after finding what P inverse is equal to, so you actually just multiply P times our matrix A that we started with times P inverse, which you would have to find. You will get this diagonal matrix 1, 2, 3. And I don't have to do like any multiplication or anything like that to know that this is true because I trust that the work that I did up to this point was correct. And so, yeah.